All right, everyone, we'll take a look at our homework that we had assigned for yesterday. It was 2 bits of it. It was the speed velocity worksheet that we gave you towards the beginning of class, and then it was the worksheet that we had that related to the video that we watched toward the end of class. We haven't gone over question number 6 yet. Let's do that now, number 6 from the worksheet, and then we'll spend some time going over that video worksheet as well, okay? Number 6 says a car travels 90 kilometers per hour east for 10 minutes, then west at 100 for 30 minutes. Calculate the car's average speed and velocity. This was a lot like question number 5. Question number 5 said you go this far in this amount of time and then this far in this amount of time. What's the average speed and velocity? This one almost seems a little bit easier. Almost. Okay, why does it seem a little bit easier? Almost. You want to find an average speed. We've got 2 different speeds here. Then maybe what we can do is just say 90 plus 100 divided by 2 is 95. Is that right? Is that right? Can we do that? No, we can't. Spencer, why can't we do that? That's right. My time intervals are different here, 30 minutes and 10 minutes. Okay, that only works if those time intervals are the same, and they're not very often going to be the same. So we've got to be familiar with the other way of doing it, because most times we're going to have to do it the other way. Look, if we want to find the average speed, then we need to get the total distance, right? Because speed is distance over time. The average velocity is displacement over time. So we've got to be able to get the total distance and the total displacement here in order to solve these questions here. Now let's break it down into 2 sections because we were going at 90, then at 100. In stage A, velocity is 90.0 kilometers per hour. We're going to say that east is positive again. Let's call it, I want to call it A or 1. I kind of like numbers for subscripts. V1. What did you guys call it? V1 or VA? V1? It doesn't matter. Call it VX and VY for all I care. Okay, put some Greek letters in there if you want. I don't know. Do whatever you want. Call it whatever you want, as long as you distinguish stage 1 from stage 2. V1 is 90, positive because it's to the east. T1 is 10 minutes. We're going to say that V2 is 100 kilometers per hour, but it's to the west, so we're going to make it a negative value. And T2 is 30 minutes. Now, technically, hours and minutes are both units for time. But the problem that we have here with using hours and minutes is that we can't really multiply those together. We can't do anything with them because we have to be consistent within a problem. Either use hours or minutes, or seconds for that matter. My suggestion would be to convert these to hours. 10 minutes is 1/6 of an hour. 1/6 of an hour is 0.16667 hours. Does that make sense? Is that okay? How many people did it that way? How many people went to hours? Okay, how many people went to minutes? How many people went to seconds? Okay, those are all fine. Okay, those are all fine. If you go to seconds, the only thing is you've got to convert this to meters per second, so it's a little bit more work, not much. 30 minutes, this one's easy, 0.50 hours. Now, my problem when I'm trying to find distance over time or displacement over time is that I don't know what the distance or displacement is in either of these sections. So I've got to find it. Let's take this equation and rearrange it. The t goes up by multiplying, right? Multiply both sides by t. I get v times t equals d over t times t. T cancels on the right side. And I get d is equal to v times t. So within stage 1, let's get the displacement now. We're going to say 90 kilometers per hour times 0.16667. That's going to give me 15. Is that right? Anybody have that number? Is that 15? 15.3? I think it might be 15. Exactly. Okay, I'm glad you said that, actually. 90 times 0.17 gives me 15.3. Let's use the unrounded number. Let's go to 4 or 5 or 6 decimal places because it's not a final answer. Okay, so let's not go 0.2, let's not go 0.17 or 0.16, let's go 0.16666. Do whatever your calculator shows. Okay, when we do that, it should work out to be exactly 15 kilometers. Okay, so you've done it right there. That's okay. Just next time, remember not to round it to 1 or 2 decimal places. Let's find the displacement in stage 2. It's going to be V2 times T2. What do we got there? This one's going to be negative 100 times 0.50. We're not going to disagree on this one, right? This one's going to be 50 kilometers, or negative 50 kilometers, I should say. Now let's get that speed, that average speed over the entire trip, by adding the two distances. What am I going to add here? 15 plus neg 50 is neg 35. Is that right? Is that right? Yes or no? Neg 35 for the distance. Who votes yes? Who votes no? Okay, the answer is no, you're right. Why is the answer no, Kate? Yeah, right, it's a scalar. Distance is a scalar, so we don't pay any attention to direction. 15 plus 50 is 65 kilometers. And you divide that by, what is it, 0.66667 hours. Okay, when we do the division on that one, it should work out, I believe, to be 97 point, no, that's not right. What do we get there? Is it 97.5? Where did you get that? 97.5? Technically, it should be 2 digits, 98 kilometers per hour, because this is 2 digits, and this is 2 digits. But we're not going to lose any sleep over that right now. Okay, the answer in meters per second, by the way, for those of you who did it that way, was 27.1 meters per second. Right? Is that okay how we did that? Question B isn't very hard anymore, now that we've done as much work as we have. B is the average velocity, and that's simply going to be displacement over time. The displacement is neg 35 meters, 15 plus negative 50. The time is still 0.667 hours. Notice, Spencer, I went 4 or 5 decimal places, right? Divide those two numbers, we're going to end up with negative 52.5 or negative 53 kilometers per hour, or it would be 53 kilometers per hour to the west, if you wanted to express it that way. In meters per second, it works out to be neg 14.6 or neg 15. How many people got that one right? Okay, good. Okay, I hope that makes sense to everybody else here now. Let me know, please, if it doesn't, so that we can spend some more time on that. All right, let's take a look at the worksheet from the video that we saw yesterday now. You guys remember this, right? Vin Diesel, his name was Xander in the movie. He was dropped off from an airplane. Then he snowboarded down the mountain, and he blew up part of the mountain and caused an avalanche, and it all turned out good. All the bad guys were dead, and Vin Diesel clawed his way out of the snow, and he was all good. Okay, got to snowboard down fresh powder. All of these questions relate to that video. Question 1 said, according to the Guinness Book of World Records, the fastest recorded speed for a snowboarder is less than 50 miles per hour. I mean, that's pretty fast, right? That's pretty fast. That's still approaching 100 kilometers per hour. Assume Xander is the world record holder and that he can snowboard this fast. What is his speed in meters per second? Does anybody have a value for that? Anybody think that they have the answer for that? Actually, I think we did this one yesterday in class, didn't we? First question. Okay, we'll do it again here. What was the answer? Yeah, 22.2 meters per second. Let's show you how we did that. The first thing that I want to do is convert miles per hour to kilometers per hour. I don't know how to convert directly miles per hour to meters per second, but I do know how to convert kilometers per hour to meters per second and miles per hour to kilometers per hour. So let's do 2 conversions here. Let's say 1 mile per hour is equal to 1.6 kilometers per hour. we've got 50 miles per hour equals x kilometers per hour. Now what I want to do here is cross multiply to get the x on the top. It becomes 1x equals 50 times 1.6. X ends up being 50 times 1.6. Divide that by 1. We end up getting 80 kilometers per hour. Now, if I want to convert kilometers per hour to meters per second, let's convert kilometers to meters first of all. That's 80,000 meters over, let's convert hours to seconds now, 3,600 seconds. There's 80,000 meters in 80 kilometers. There's 3,600 seconds in 1 hour. That gives me a speed of 22.2222 meters per second. I'm going to use the unrounded number here because I'm probably going to need to use this number somewhere down the road. Okay, so let's keep it 4 or 5 decimal places. Number 2 is not a math question. That's why you had a little bit less space to answer it. A typical power avalanche moves at a speed of between 60 and 90 meters per second. Is it possible for Xander to outrun the avalanche as in the movie clip? Explain why or why not. Why not? The answer, yes or no. Could he outrun it? If his maximum speed is 22 meters per second, okay, and this is the maximum speed of the world's fastest snowboarder, okay, and the avalanche runs at a minimum speed of 60 meters per second, is he going to outrun it? No, he won't. He can't, because it's moving at its minimum, it's moving almost 3 times faster than he is. So the answer is clearly no for this one. He can't outrun it. Just because it's in video doesn't mean it can actually happen. They lie to us like that. Don't you hate that? Number 3, this is the tough question right here. Assume Xander is snowboarding at the record speed of 50 miles per hour. In other words, 22.2222 meters per second. And the avalanche is moving at the lower limit of 60 meters per second, and that Xander gets a 10-meter head start on the avalanche. How much time would elapse between the time the avalanche starts and the time that it catches up with Xander? It's a tough question. Okay, conceptually, it's a tough question. Mathematically, it's easy. But to get to the math is the tough part here. Anybody have any suggestions of what I should do for this? The avalanche needs to gain 10 meters on him, right? The avalanche needs to gain 10 meters on him. It's 10 meters behind. So if Xander travels 100 meters, it needs to travel 110 to catch up. If Xander travels a kilometer, it needs to travel a kilometer plus 10 meters to catch up. If Xander travels 5 meters, then the avalanche needs to travel 15 meters in order to catch up to him. Does that make sense? If Xander is standing still, then the avalanche needs to travel 10 meters to catch up to him. So the avalanche needs to travel relative to Xander 10 meters. The distance covered by the avalanche relative to Xander is 10 meters. Now, if we're going to use the distance, not that it has to travel overall, but the distance relative to Xander, then we need to use the speed of the avalanche as well relative to Xander. What's the speed of the avalanche relative to Xander? What is it? Yeah, close, 37.777, right? And we're going to get that by saying 60 kilometers per hour minus 22.22, 37.77778 meters per second. Right, relative to the ground, it's traveling at 60, but relative to Xander, because Xander's moving as well, it's only going at 37.7. That makes sense? So if he has to make up 10 meters, travel 10 meters relative to Xander, and he's going at 37 meters per second relative to Xander, how much time is that going to take? We get distance over time. Let's take the t up by multiplying, right? Multiply both sides by t. Oops, that doesn't cancel. Okay, these two t's cancel. I'm left with d is equal to v times t. Now let's take the v down by dividing, okay, both sides. V's cancel there, and I'm left with t is equal to delta d over v. The distance traveled here is 10 meters. We divide that by 37.77778, and we get a total time here of 0.2647 seconds. So we watched, I don't know how many minutes of that clip yesterday, several minutes of the clip, probably 3 or 4 minutes of him outrunning this avalanche. How long could he outrun this avalanche? 1/4 of 1 second before it buried him. That is, if the avalanche is going really slow, and if he's going as fast as this snowboarder has ever gone. So the odds of him outrunning it for even 1/4 of a second would be close to 0. How far would Xander travel before the avalanche caught up with him? Well, he's traveling at 22 meters per second. Relative to the ground. And he travels that far for 0.2647 seconds, and multiply those two numbers together, 5.9 meters. So let's assume this is where Xander is. Okay, when he throws that dynamite to start the avalanche, cause the avalanche to occur, he would get to about here, from that wall to here, before he was completely buried by the avalanche, as opposed to going all the way down the mountain. Okay, that's why you probably shouldn't try to outrun an avalanche. You probably shouldn't throw dynamite on the side of a mountain either. That's probably your first mistake. The second mistake is trying to outrun it. 5, I like this question. I don't know if how many of you caught this one. It's interesting that Xander is able to hold on to the antenna as the avalanche passes over him, and he's able to dig himself out. There's a very clear indication earlier in the clip that an avalanche has far too much kinetic energy for this to ever be possible. Did anybody catch what that indication was? Yeah? Yeah, I mean, it obliterated that house, right? Okay. You see this antenna is blowing in the wind before the avalanche ever hits it, going back and forth in the wind, yet somehow it withstands this avalanche. He's able to pull himself out. Okay. It would be impossible, obviously. And 6, is it ever possible to outrun an avalanche? I'm sorry? Right, but if the world record holder has gone 22. Okay. For all practical purposes, is it possible? Smart Alec. No. The answer is no, okay? The answer is no. I mean, is it theoretically possible? Of course it is. Of course it's theoretically possible. Is it ever going to happen? No, it's not ever going to happen. We're good at that? We're going to shift gears a little bit now and start talking about some graphs that will help us in analyzing certain problems involving position and time. In other words, involving velocity. Okay, the first thing that I want to do is show you some different shapes of position time graphs. By the way, whenever you see a graph, I'm not sure if you've learned this in Science 10 or not, whenever you see a graph, there are 2 variables on that graph, the manipulated and responding variable, always. Okay, control variables never on that graph. The manipulated variable will always be the x-axis. So in this case, when you get position versus time, time is the manipulated variable, position is the responding variable, always. Okay, always. Always remember that. Now, we've got a series of 5 position time graphs here. I want to first of all take a look at what each of these represents. Okay, what's happening in each of these graphs. First one, we've got a straight line position time graph. Who can tell me what's going on here? The object that's represented by this graph is doing what? Good. It's going at a steady pace or a constant velocity, right? The position is increasing. It's getting further and further and further away from where it started, but it's doing it because it's a straight line at a constant rate. And if it's changing its position at a constant rate, then that must mean that it's going at a constant velocity. It's not speeding up and it's not slowing down. What about the next one? This one's a bit tougher. It's also a straight line, but it's a straight horizontal line. You can tell me what this one represents. You got an object in this graph here, represented by this graph here. What's this object doing? Nothing. It's at rest. It's not moving. It's stopped. You could also say it's a constant velocity because it's a straight line, right? But it's a constant velocity of what? A constant velocity of a value 0 meters per second. It's easier to say it's stopped. Look, we know this because the position is not changing. The position here is a certain value. The position here is a certain value. The position here is the same value. It's stopped. It's not moving. What about this one? Also a straight line, but this time sloped downwards. This one is what? You said a minute ago a straight line represented constant velocity, right? This is constant velocity as well, right? So why do we put this one and this one? Is there anything to distinguish those two? Yep. Please. Yeah, it's a constant negative velocity. In other words, it's coming back towards its initial position. So if this one represents me driving to Calgary, this one represents me driving back to Okotoks. Does that make sense? Constant negative velocity. What a lot of people will do when they look at this one and say, oh, it's going backwards. Be careful with that. Okay, it is going backwards in the sense it's going opposite to the direction that it is in the first diagram. But sometimes when we say that, we start thinking, okay, the car's in reverse. It's literally driving backwards. It's backing out of a parking stall. Okay, the car doesn't have to be going backwards. The car can be driving forwards, but simply in the negative direction, opposite to the direction that it's moving in the first one. How about this one, the next one? This one's curving upwards. Yep. Yeah, it is. Good. You're coming at that from a math perspective here. Right? The x value is an exponent. In fact, in a couple of days, I'm actually going to show you an equation so that you can actually see that. Okay, for now, let's look at it more conceptually as opposed to mathematically. That's a good answer, though. Really good answer. It's probably a little bit further than we want to be with it right now, though. It's accelerating. Yeah, it's accelerating. In other words, the x value does have an exponent. The x value is increasing, or the position. The y value is increasing quicker than the x value. Okay, so let's say it's accelerating. The position is getting bigger, but as time goes by, the position is getting bigger quicker, if that makes sense. Okay, at 1 second, the position is getting bigger. It's going further, but at 5 seconds, it's going further quicker. So it's accelerating. And what about this last one here that I have drawn, where it's curving and going upwards, but curving downwards? What would that mean? Accelerating backwards? No. This one is, the position is still increasing, right? It's still getting further away from where we started. It's not coming back to where I started. If I'm driving to Calgary, okay, I'm driving to Calgary the entire time here. I'm not turning around and going back because the position is positive and getting bigger every moment. So what's happening there? I'm sorry? Decreasing speed. Good. We're driving to Calgary, but as we go to Calgary, we're slowing down. Still moving in the positive direction, but slowing down. Okay, let's say decelerating or negative acceleration. Or as you said, it's decreasing velocity. That would be okay as well. Now, I don't want you to memorize these shapes. Okay, I don't want you to memorize what each of these means. I want you to use some logic. Okay, I want you to take a step back from it when you see one of these on a quiz sometime. And I want you to think, okay, wait a sec. The position is increasing. Still, it's going positive, but it's not going as quickly as it was down here. So it's decelerating, it's slowing down. In this one, the position is staying the same. If the position is staying the same, then the object is stopped. Let's think about each of them. Okay, understand each of them. And that way there's less to remember, okay? There's a lot of stuff we got to remember this year. If we can figure out something, that's even better because it means there's less to remember. And I don't know about you, but I'm terrible at things like that, remembering things. All right. Now we do have some calculations that we're going to have to do on these graphs as well, these position time graphs. I'm going to show you, first of all, how to find position and displacement. Those are the easy ones, position and displacement. Whenever you're trying to find a variable that is on one of the axes of the graph, then there's not going to be a calculation. It's just going to be reading it straight off the graph. Position is on the y-axis. Displacement isn't, but displacement is almost on the y-axis because displacement is simply defined as the change in position. You want to find a position on the graph? Okay, all you're going to do is go up and over. I want to find the position at 5 seconds. Let's go up at 5 seconds. Let's go over. Let's read the value of that position. Okay, the position at 5 seconds is simply up and over. The position at 2 seconds is up and over. The position at 10 seconds is up and over. The displacement is up and over again, then subtract them. Because displacement is simply the change in position, the final minus the initial position. So if we can find the position by going up and over, let's do that twice. Let's get the position twice and then subtract the two. So for instance, if I wanted to find the displacement between 2 seconds and 8 seconds, then I would go up and over. That's my initial position, di. I would go up and over again. That's my final position, df. And then I would subtract those two numbers to get my displacement, the change in position, how far it's traveled. Okay? Does that make sense, guys? You guys have done this graph stuff before, right? Science 10 a little bit. Okay, even Math 9, I think you did it in Math 9. Not necessarily position time graphs, but graphing skills in general. The next one is the tricky one here. We used to teach in Physics 20 just the answer to this question, the average velocity on a position time graph. But I want to show you how we get that answer. Okay, I don't want you to just trust me that the average velocity is found by doing this. Okay, I want you to see how it actually happens. So what I want to do here is, first of all, tidy this graph up. And then I want to write down an equation that represents this graph. Who can tell me which equation represents any straight line graph? Think back to math class again. Which equation represents any straight line graph? You guys know this, yeah, Luis? No. That would represent a very specific straight line graph, but not any straight line graph. Remember this one, guys? Y equals mx plus b. Remember that? You guys have learned that before, right? Yes, y equals mx plus b. The y-axis of this graph, is position. The x-axis of this graph is time. What does m stand for? What is it? Slope. I'm going to write the word slope in here. I could leave an m for the symbol, but I don't want to get mixed up with mass. Okay, I don't want to get it mixed up with mass. Right now, we haven't even learned about mass, but as we go on this year, you will see mass. Now, I'm going to simplify this a little bit. I'm going to cheat a little bit here. Okay, as we go on in the year, we won't cheat like we are going to right now, but it's okay. It's okay right now. B stands for what? My goodness, your Math 9 teachers wouldn't be happy with you guys right now, right? Yeah, it's the y-intercept. In this case, it's going right through the origin, so there would be no y-intercept, right? This graph could have a y-intercept. I'm going to cheat a little bit right now because in this particular one, it doesn't. So I'm just going to cross it off. Now what I want to do is get an equation from my data sheet that has the same variables in it. How about v equals d over t? I'm going to rearrange it. D is equal to v times t. Now understand that position and displacement aren't quite the same thing. Okay, they're not quite the same thing, but for our purposes here right now, and this is where I'm cheating a little bit, we're going to pretend that they are. Okay, they're almost the same thing anyways. In fact, in this particular graph, they would end up being the same value. I want you to cross off displacement position because it appears in both equations. I also want you to cross off time because it appears in both equations. What am I left with in this first equation? Slope. What am I left with in the second one? Velocity. If you want to find the velocity on a position time graph, calculate the slope. Does that make sense? Yes? You guys remember how to get the slope? I don't know if I'm real optimistic that you do remember with the way that you've answered my questions here earlier on this graph. Yeah, Dustin? Yeah, it's rise over run. Pick 2 points on the line far apart and go y2 minus y1. That's this value minus this value over x2 minus x1. This value minus this value. I'm going to show you a little bit later today a nice little trick for finding the slope with your calculator where you don't have to actually do rise over run. Okay, there's a cheat on your calculator that allows you to find that. What do you think this means? The instantaneous velocity. It's the velocity right now, or right now, or right now. It's the velocity at one specific moment in time. Now, if it's a constant velocity, if it's a straight line, and therefore a constant velocity, then the instantaneous velocity will be the same as the average. Let's think about it. If the average velocity over this graph is 5 meters per second, then the instantaneous velocity right here must be 5, and right here must be 5, and right here must be 5, and right here must be 5. It's a constant. So if the average is 5, then the constant velocity at any spot must also be 5. The hard one is this one, right? The hard one is this one, because this is the one where we have to actually do a calculation. Okay, this one's up and over. This one's up and over, and then subtract, so it's a bit of a calculation, but an easy one. This one, well, there's a calculation involved, but we've already done it right here. This is the one where we have to do the real calculation, the slope of the graph, rise over run. Right? I want to give you an example here. The example is a straight line graph, again, a constant velocity, but you know from the shapes that this would be a constant negative velocity, right? A constant negative velocity. It's not slowing down. That doesn't mean it's slowing down at all. It means it's going at a constant velocity, but it's like it's coming back from Calgary as opposed to going towards Calgary. We have 5 questions that we have to answer here. What is the position of the object in the graph to the left at t is equal to 10 seconds? What do you do to find position? Remember, when you want to find something that's on one of the axes, all you're going to do is read it right off the graph. Okay, you want to find position, which is on the y-axis, go up and over. At 10 seconds, we're going to go up and over. The position there is 30 meters to the east. Does that make sense? Good? What's the displacement of the object in the graph between 0 seconds and 10 seconds? Well, Displacement is the final position minus the initial position. The final position at 10 seconds is 30 meters. The initial position at 0 seconds is 80 meters. So 30 meters minus 80 meters is neg 50 meters. Or what else could you say besides neg 50 meters? Neg 50 meters is fine, but what else could you say that would also be correct? 50 meters to the west, right? Either one of those would be fine. Let's get the average velocity in the graph to the left between 0 and 10 seconds. Well, we're going to take the slope of that, right? Slope is equal to y2 minus y1 over x2 minus x1. Let's pick 2 points on the graph. Let's pick the beginning and the end. y2 is 30. y1 is 80. x2 is 10. x1 is 0. So we're going to say 30 minus 80 over 10 is going to be neg 5. Neg 5 meters per second. What else could you say? Not neg 5, but pos 5 to the, somebody said it before, James, to the west. Pos 5 to the west. Good. What is the instantaneous velocity at 2 seconds? Look, if it's 5 meters per second to the west over this entire trip, then at 2 seconds, it's also going to be neg 5 meters per second, or 5 to the west. What about at 7 seconds? Well, if it's neg 5 the whole trip, then it's got to be neg 5 at 7 seconds as well. So no calculation involved in question 4 and 5. How's that? That make sense? Here's what I'm going to leave you with tonight for homework. Okay, the other side of that worksheet has 4 questions. I would like you please to do the first 3 questions for homework. Questions 1, 2, and 3. Got it? So flip the page over, questions 1, 2, and 3 for homework tonight. They all go exactly the same way as this example has gone. Keep that example beside you. Okay, when you're working on these questions, keep the example beside you and keep that little page of notes beside you as well. It's okay to refer back to that. If you don't remember how to find velocity, you got to look at it and say, oh, yeah, it's slope. That's okay. Okay, this is not a quiz or a test. Okay, it's okay to look back in your notes. In fact, you should if you're having trouble with it at all. See what you can do there for tomorrow, and then we'll take a look at it then.